Okay, let's get this started. Welcome to our seminar, everyone. Today is our great pleasure to be able to invite Professor Molei Tao give us a talk. Professor Tao received his PhD in control and the dynamic system with a minor in physics from Caltech. And then after that, he worked as a postdoc in Caltech as well, then moved to NYU as a Quran instructor. Starting from 2014, he has been working as an assistant professor, then now associate professor in the School of Mathematics and Machine Learning Center at Georgia Tech. His work received numerous recognition, including a recipient of WP Carey PhD prize in Applied Mathematics, American Control Conference Best Student Paper finalist, the prestigious NSF Career Award, AI Stats Best Paper Award, IEEE EFTF IFCS Best Student Paper finalist, and more recently, Coulomb-Pack Scholar Awards. So without further ado, Molei, please.
Thank you so much for the very generous introduction. And also, I really appreciate this opportunity to speak here. So thank you so much, Rongjie, for the kind invitation. So what I'm going to talk about has a very long title, but basically, I want to introduce to you some of the possibilities of exploring interactions between machine learning and nonlinear dynamics. So if you go from the left to the right, obviously, you can use machine learning to solve dynamical problems in sciences and also scientific computing. Also, going in the other direction, so from right to the left, we can actually use dynamics to help machine learning. More precisely, you can actually design and analyze, various optimization, sampling, and deep learning algorithms. And in fact, in today's talk, I'll focus on at least half of the talk on analyzing deep learning algorithms using dynamics. In particular, I'll actually quantify some of the effects of large learning rate. And these are actually good effects. So a large learning rate can actually provably give you better training accuracy as well as test accuracies, as you will see. And then there's also another aspect that I'll talk about, namely how we can actually use dynamics to design better optimization algorithms. So in part 2 of my talk, I'll actually be designing an algorithm that optimizes functions that are actually defined on the manifold. I'll focus on a very special manifold called Stiefel manifold for reasons you will see very soon. And the way we do it is we will first construct dynamics that evolve in continuous time that actually does the optimization on the manifold. And then I will discretize the time of this dynamics very carefully so that I actually stay on the manifold while doing the optimization. So that's roughly the plan. There are things that I won't discuss today, but are very interested in. For example, machine learning for dynamical problems and scientific computing in general. So if this is something that you're interested in, I'd love to talk more offline. And also there is something else that we actually spend a lot of time on. So it's basically the problem of sampling and also optimal transport and generative modeling. And again, if you're interested in this, I'd really appreciate an opportunity to talk more offline. But without further ado, let me start talking about some of the understandings that we can gain from dynamics in terms of understanding supervised machine learning. So in supervised machine learning, the paradigm is usually the following. So you have training data set, which consists of data points that are basically pairs of labels. So for each data point, you have an input label and also an output label. And by the way, just making sure, can the cursor of my mouse be seen? Or
yes.
it's...
Yes.
Okay, thank you. Thank you. So the thing that people typically do is they will actually choose a model, for example, a deep neural network modeled by this function G that has a parameter, which in the case of the neural network corresponds to the weights and biases of the neural network. And then the goal is to basically find the best parameterization of the model such that the output predicted by your statistical model matches the output label of the training data set as much as possible. So obviously, this training process boils down to an optimization problem where you want to optimize this empirical loss f over possible parameters. And there is one problem, which is that, okay, so if you use a very expressive model, for example, a neural network, then this G function is actually non-convex. And the overall loss function, f, is also non-convex. And oftentimes, when you do the training, when you do the optimization iteratively, you can actually get trapped in a local minimum. And this is actually bad, because that means that you actually have a better X that gives you a much better match with the output label, but you can't get there. So you actually get suboptimal training accuracy. In part 1a, I will argue that if you use a large learning rate, then you can actually escape the local minimum, and therefore provide and therefore be able to actually solve this problem partially. But that's not the end of the story. So after the training phase, you also have a testing phase. So there you already have some value that you get out of the training. So you have this X trained, and then you are given new data, so new tested data, and you hope that the prediction that you get from your trained model will be as close as possible to the hypothetical output label of the tested data. And if you compare these two, the training accuracy and the test accuracy may not necessarily be the same. And in fact, what you choose as your X matters. So imagine an easy situation. So suppose you are already at a global minimum. Your choice may still matter because there can be actually multiple global minima, and each one may actually give you a different test accuracy. So this the difference between training and test accuracy is roughly called generalization, and of course we want to converge. We want our training process to converge to a point that has good generalization. So we hope it generalizes well. And in part 1b, I want to argue that if you use a large learning rate, you can actually converge to a point that generalizes well, generalizes better than other points. So that's roughly speaking the plan for part 1. And let me start by telling you more details. So so the first one, namely on the escape of local minimum, is based on this work published in a machine learning conference joined with my student Lin Kai Kong. And the goal is very simple. It's just to minimize this function, and gradient descent is what we will focus on. So it's a very simple iterative method. And if you actually run gradient descent with a small h, so a small learning rate, you get basically this behavior. So monotonic convergence to a local minimum, which in this case is also the global minimum. If you make h much bigger, you can still have convergence, but the convergence is actually not monotone. So you have this oscillatory behavior. If you make h even bigger, then you get instability. So you're not converging to anything. You actually have iterates blowing up to infinity. So you may say, okay, fine. So I agree that different time steps, different learning rates will give you different results. But how is this relevant to machine learning? So what if the potential landscape that we previously saw was just a microscopic part of a multi-scale potential landscape, and then I'll basically do gradient descent again with a large learning rate, and where and this red dot basically indicates the location, the value of x being given by the location of the particle in this potential well. And then you see this particle really bounces around in a rather random fashion. So it's very hard to predict where it'll end up at in the next step. And in fact, I plotted the trajectory of x. So this is just a single trajectory. So x is a function of the number of iterations, and this is the orbit. And you see, this is, if you're familiar with stochastic processes, you would feel like this looks like stochastic. Even though I want to remind you, gradient descent is a completely deterministic algorithm. So there's nothing really stochastic about it. And furthermore, if you feel like this is stochastic, then the statistical mind of yours probably will urge you to actually collect values that x takes along this trajectory and plot the histogram of values. And this is what I did, and then I get something like this. And then you may say, oh, this looks like a pretty nice distribution. In fact, it really is. And in fact, if I run longer, the distribution will become nicer and nicer. And this is some of the things that I'll quantify later on. But at this moment, you see something. So you see at least something qualitative. So the deterministic dynamics of gradient descent nevertheless exhibits behavior that looks like stochasticity. And in fact, if you're familiar with stochastic gradient descent, which actually has intrinsic stochasticity, it seems that what we get here is very similar to what you get in SGD. So what's going on? So we actually have a quantitative theory. So the theory says, okay, so if the objective function is actually multi-scale, and also my gradient descent is actually used with a large learning rate, then the dynamics of gradient descent, albeit being deterministic, is actually chaotic. So that's why you will see behaviors that looks like stochasticity. So what do I mean by a multi-scale objective? So I require the objective function to be the sum of a macroscopic part that could, for example, look like this, plus a microscopic part that is characterized by a small parameter epsilon that is much smaller than 1. So an instance of a microscopic structure is that you take a periodic function, you squeeze it in the x direction by division by epsilon, and then you squeeze it in the y direction by multiplication by epsilon, and then you add this function on top of this macroscopic potential, and then you get a multi-scale one. Okay, so you basically create a microstructure that is periodic in this case. And of course, people will say, oh, this is a mathematician's fantasy. In reality, a function, you will never have a function that has a microstructure that is this regular. Well, it doesn't have to be this regular. So another example that we can work with is something called a quasi-periodic microstructure. So you see, the microstructure just looks more regular. So if you don't know what a quasi-periodic function is, it doesn't matter. We don't need this either. So all we need is actually some very mild condition. Roughly speaking, so I require the micropotential to have a gradient that actually converges to some random to something. And so I require basically my first order derivative to have an order 1 weak limit. And by the way, you can check this. You can actually show this is true for example, the 2 examples that I had above. So after differentiation by 1 time, this epsilon basically cancels with the epsilon outside. So you actually get an order 1 term. And there is another condition, which is second order derivative being order 1 over epsilon, but that's also not a very strong assumption. So that's roughly speaking my definition of a multi-scale objective function. What about a large learning rate? So remember, we're doing gradient descent iteration. So basically, I'm iterating this map, and because my potential, my loss function is multi-scale, so it can be rewritten like this. And let me first explain what would be a small learning rate. So in traditional optimization theory, it's well known that if your learning rate eta is less than 1 over L, where L is the Lipschitz constant of the gradient, then you basically have guaranteed convergence. So in this case, because of this microscopic gradient, you can actually work out the Lipschitz constant. It's going to be 1 over epsilon. And what that means is if your learning rate is smaller than epsilon, then you will just converge to a local minimum. In fact, that is close. That is the closest to your initial condition. So in this case, I mean, everything is sort of boring. So your step size is small enough so that it actually resolves all the scales in the problem, and then you will just have guaranteed convergence to the closest minimum. What would be a bad minimum? What would be a bad learning rate? So if the learning rate is very big, then you can't even resolve the large scale. So if you're a computational mathematician, you may think, okay, so this F1 gives you stiffness. The more derivatives you take, the bigger values it'll give you. But even if you get rid of this as F1, there is still a limit under which you can take your learning rate at. So if the learning rate becomes too big, even if you iterate just the macroscopic gradient, you will get instability, let alone that you have this microscopic one. However, in between these two ends of the spectrum, you have a lot of space. So, so in fact, as you keep on increasing eta, you will first enter a regime. By the way, so this space in between is what I call the large learning rate regime. But in fact, it can be subdivided. So as eta keeps on increasing, you first will enter something that I call a local chaotic regime. And then as eta further increases, the chaos will become global. What do I mean by these? Okay, so so remember, gradient descent is really just the iteration of this map.
Molei,
And yes.
Can I have a quick clarification of that constant 1?
Yeah, please.
Is that universal constant or does it depend on F0?
1.
The constant.
It depends. Yeah, it depends on F0. So this is like, so this is like 1 over the Lipschitz constant of the gradient of F0.
Okay.
Yeah, thank you. This is a very important clarification. And by the way, please stop me at any time if there's anything unclear. Okay, so the deterministic gradient descent is an iteration of this map. So you can view it as a dynamical system in discrete time. And then you can talk about the attractors of the dynamical system. So in fact, in a neighborhood of a local minimizer, which is basically illustrated here as the y-axis, the local minimizer is going to be a stable fixed point of this iteration when eta is very small. And as you increase eta, this fixed point will remain as a stable fixed point for a very long time. But at some point, you can prove that it'll lose its stability. So as eta continues, this local minimizer is still a fixed point, but it's no longer stable. And instead, nearby, there will be a periodic orbit of period 2 that emerged. So what I mean by that is that, okay, so if you start right here, you iterate 1 time, you will converge to, you will go to a point that is right here. And then if you iterate 1 more time, you will go back to the starting point. So you have a periodic orbit of period 2. And this is actually going to be a stable attractor in the neighborhood. And as you keep on increasing eta, you will undergo something that is well known in dynamics called period doubling bifurcation. So the period of the stable attractor actually keeps on doubling very quickly. And in fact, in finite time, after finite increase of eta values, the period actually becomes infinity. And then the system actually transitions into chaos. So at this moment, I want to emphasize that X actually still stays within a microscopic potential well. So these 2 dashed lines are actually the boundaries of this potential well. You can see, the area is actually very small. So the width of the small scale potential well is actually order epsilon, and so is the height. And in this case, you have a universality theory. So you have a well-known tool called unimodel map, which helps you understand the chaotic dynamics inside this potential well. But you have a problem. So if eta further increases, as you can see, you feel like eventually this chaotic sea will flood over the boundary of this potential well. And that's exactly what is going to happen. So if you start, for example, right here, you know your potential has a gradient that is pointing to the right. And if you pick eta to be large enough, what happens is obviously then you would just go out. So you can actually escape the local minimum if eta is large enough. So as eta further increases, you actually enter a regime that I call a global chaotic regime. So this is the most interesting situation. So for example, we can prove the following result. So if F naught, the large scale potential is strongly convex, C2 and L smooth, then the iterations of gradient descent actually no longer converges to a point. It actually converges to a statistical distribution. And we can actually quantify this limiting statistical distribution. It's almost like Boltzmann-Gibbs distribution. But there is actually a correction. So it's not exactly Gibbs distribution, but it's very close. The justification of this is actually very interesting, but it's pretty non-trivial. So I'm happy to tell you more offline. But instead, let me show you the implication of this result. So okay, so here is a toy illustration just to fix the idea. So the actual loss function may look like this. Okay, so large scale potential polluted by microscopic ones. And what you have in this limiting distribution is only F naught. You don't even see this F1. You don't see the micro scale. So F0 actually looks like this, and therefore you will actually just be sampling from a distribution given by the corresponding Gibbs distribution. So this F0 basically gives you this red distribution. And you can start with arbitrary initial conditions, say this uniform distribution, and after sufficiently many iterations, for instance, you will converge almost to this limiting distribution. And it doesn't even depend on what your initial distribution is. So what this means is that, okay, so if you iterate gradient descent in this potential landscape with a large enough learning rate, you don't even see these small bumps. Okay, it's like driving a car that is very fast, and then you don't see the imperfections of the road. But this result is more profound. Well, this result is more than just that intuition, because if you just wipe out all these local minimum, and then you do gradient descent, you will actually converge. So if you do gradient descent with F0, you will converge to the global minimum in this case. But you don't because of F1. You actually converge to a statistical distribution generated by F0. Okay, so this is why this is actually very interesting. And this is actually a quantitative mechanism of escape from local minimum. It's completely due to the fact that you use a large learning rate. Okay, so there's no noise, there's no stochasticity because I actually use the full gradient. So in machine learning, typically people care a lot about escape from local minimum, but usually they think, okay, so you use a stochastic gradient, and therefore the gradient is actually giving you some noise, and the noise actually helps you escape the local minimum. Here, this is a completely parallel mechanism of escape. It's completely deterministic. It's really just an effect of a large learning rate. And also you may wonder, what if F naught is non-convex? So this is more complicated. We actually have theories as well, but for the sake of time, let me instead answer a different question. So people may say, oh, again, okay, mathematicians coming up with another so-called machine learning paper. Do we actually have multi-scale potential? Do we have multi-scale loss function in real problems? And the answer is yes. So we have both empirical and theoretical results. So for instance, okay, here I'm simulating a small neural network on a small data set using large learning rate. And a lot of information can be read from this picture, but for instance, let's focus on this one. So this is the trajectory of one of the parameters of the neural network. So as time increases, this parameter actually doesn't converge to a point. So if you see a line that it actually converge, if you see a horizontal line that it converges to a point, but then you see this blob, And this blob is actually the support of this parameters distribution, probability distribution. Okay, so you actually have a statistical convergence. And there are other things. I mean, histograms of the distributions, which are roughly speaking saying that, okay, so you are actually sampling from a very non-convex distribution. But let me not bother you with too much detail. What about theory? So the idea is very simple. So the reason that you can possibly have a loss that is multi-scale is because maybe your training data is multi-scale. So honestly, for most of the time, this is the case because the data usually is distributed around a mean, but with smaller fluctuation. So so the data might be multi-scale, and the idea is that maybe the loss will inherit a multi-scale structure from the data. If you think about this, this is still non-trivial because the loss function is a function of the parameters, say the parameters of the neural network. The data is not what you optimize over, so the data is already fixed. But you know, still you can inherit this. You can have a duality. So in fact, what we have is only very limited result. But if you have just the two layers and you have a periodic activation, then you can sort of have a multi-scale structure in the data inherited into the loss function. And then, you know, the theory that we had, the assumptions that we had actually make sense. Okay, so summarizing this part, so deterministic gradient descent can actually give you chaotic dynamics if the learning rate is large enough, and this chaotic dynamics will help you escape microscopic local minima. And the reason is because really the gradient descent dynamics no longer optimizes the loss function. Instead, it's actually sampling from a statistical distribution determined by the large scale part of the loss function. So so this matters because you know, in machine learning, of course, people want to go to deeper minimum because then you get better at least better training accuracy, and also better training accuracy is associated with better test accuracy. And then the quantitative theory that we had was basically suggesting, okay, so you actually go to you have exponentially higher probability of getting to a deeper minimum. So that's why, you know, it actually helps to escape minimum in a quantitative way. Okay, so what I'm gonna do next is I'll change gear a little bit and show you why it's possible that large learning rates will actually give you provably convergence to a flatter minimum. And the reason that I care about flatter minimum is that it's a very common wisdom in machine learning that if you have a flatter minimum, then you get better generalization. So you get better test accuracy. So basically, part 1A focuses on training accuracy, and part 1B tries to focus on test accuracy more. But it's actually you know, focusing on test accuracy in a very concrete way. So people actually are not very sure whether flat minimum really gives you better generalization. It's a belief. Some people say the opposite. I don't want to say anything about this belief. I just want to show that indeed I can converge to flatter minimum. The generalization part is the shaky part. So I'm happy to discuss more. And so this is based on another paper that is published in a machine learning conference. Joint work with my student Yuqing Wang, my former student collaborator Mingshuo Chen, and his advisor Tuo Zhao. And the problem that we consider is very special. So it's called a homogeneous model. And roughly speaking, a two-layer neural network with a very specific activation function, such as the ReLU activation, is a homogeneous model. What do I mean by that? Okay, so first of all, ReLU is a very nonlinear function, but it enjoys a very special property called homogeneity. What that means is that you can scale the input by a scalar. You can multiply the input by a scalar, and then the output will be multiplied by the same scalar, even though the function is arbitrarily nonlinear. And then because of that, because of the property of ReLU, you have this amazing property of the loss function of your neural network. So if you multiply the first weight matrix by a scalar function C, and you divide the second weight matrix by the same scalar function C, you actually get the same loss value. Okay? And this is a symmetry. It ensures, for example, you will have a continuous set of minimum. Because, I mean, if you give me a minimum, I can pick a C that is arbitrarily close to 1, and then I get a minimum that is arbitrarily close to this minimum. So I do not have isolated minimizers anymore. I have continuous valleys of minimizers that can actually intersect with each other. And some of these minima actually generalize better than the others. Again, arguably, maybe flatter ones actually generalize better than the other ones. And by the way, so by flatness, I mean, okay, so if you look at the Jacobian of, if you look at the Hessian of this objective function, that basically describes the local geometry of your energy landscape. And if you have smaller eigenvalues of the Hessian, then the landscape is flatter nearby. And the question is, which one of these minimizers will we actually get after training? At this point, I want to clarify one thing. So sometimes people say, oh, how can you dare say that you actually work on deep learning if it's just a two-layer neural network? So I agree, but unfortunately, that's the status of the field at this moment. So two-layer neural networks are already interesting enough that a lot of the problems are still not very well understood. And in fact, I'm going to do one more thing that sounds very scary, but that's also something that people in the field do very often. So I'm going to drop this activation function. I'll pretend this activation function is an identity map. And it's also homogeneous. So this whole model is homogeneous. And then you have a two-layer neural network, two-layer linear neural network, which is almost the same as another important problem in data sciences, which is called matrix low-rank factorization. So there, the problem is, okay, so you have an n by n matrix A, and you want to find a rank D approximation of this matrix. And one thing you can do is to formulate it as an optimization problem. So you pick two matrices, X and Y, that are n by D, where D can be much smaller than n. And then you try to approximate A by X times Y transpose. So you can formulate it as a minimization problem. And of course, the low rankness is automatically guaranteed. And this problem is almost the same as linear neural network. So just to give you another reason why linear neural network is already non-trivial. And in fact, let me focus on the matrix low-rank factorization problem as a model of a homogeneous problem. So this problem enjoys a lot of nice properties. So the existence of a continuum of minimizer is one. So that was just basically what I mentioned earlier. Moreover, each local minimum in this case is a global minimum. However, some of them have norms of X and Y being almost the same. So this is something we call balance. And you can prove very easily that if you have balanced norms, then this minimizer is flat. If these two are very different, then the minimizer is actually very sharp nearby. And if I do gradient descent for my minimization problem, then I wonder, well, then I get basically this set of iterations. It's nonlinear because you have basically this cubic term here and here originated from the fact that my loss function is actually quartic, so fourth order polynomial. And you see that this actually creates a lot of difficulties. For example, if X and Y are unbalanced, then one of these two terms, so maybe this one is very big, and the other one is very small. So because the first one is very big, you have to choose your learning rate, your H to be very small in order to resolve everything if you follow the traditional theory. But then the other variable makes very little progress. So unbalancedness is very bad for optimization. It's also very, very bad for theoretical analysis. What this work actually suggests is that don't worry about balance. If you make your learning rate very big, then you can start with initial conditions that are very unbalanced, and you will converge to a balanced solution. What that means can be illustrated by this simple example. So I'm plotting in 2D. So x and y are just the two scalars. A is just the scalar. This is just for illustrational purposes. So suppose my initial condition is right here. And this line, by the way, is basically the line that corresponds to x times y being equal to 1. So you see, you really have a continuum of global minimizers. Here is another branch. So if you start very nearby this continuum of minimizers and use the small learning rate, such as the one indicated by red, you basically converge to the nearby point. But if you use a very large learning rate, then you actually make a jump to here, and then you jump more. You actually follow very strange trajectories. But what is most interesting is that eventually you will converge, and you will converge to a minimizer that is very far away. But this minimizer is balanced. It corresponds to x almost being equal to 1, y almost equal to 1. Okay, so this is really an effect of a large learning rate. This is so I think I have to skip something. So this is actually very hard. I mean, if you use traditional optimization theory, it's never going to work. But we developed a whole machinery, and you have basically the same phenomena if you do full matrix factorization. So here x and y are basically both high dimensional. Well, at least the full matrices. A is also a matrix. If you start with very small learning rate, basically x and y will converge without really getting closer to each other in terms of their norms. But as h becomes bigger and bigger, you see upon convergence, you have more and more balanced norms. And that's of course because in the initialization phase. So in the iterations earlier, you actually undergo very complicated dynamics. Of course, h cannot be arbitrarily large. If h is too large, then you will just have blown up solutions. So the proof of this result is complicated. It's so basically you have to scrutinize the discrete dynamics. What I drew in the background is really just how you prove the 1D dimensional case, and then we have to generalize it to vectors and then to matrices. So really you need to be very good at understanding the dynamics, but it's very technical. So let me skip it. But in summary, so if you use large learning rate in gradient descent, you can actually get implicit bias. It's really a bias that is created by your algorithm. So this bias is very important because it actually bias towards balanced and therefore provably flatter minima. And this is of course consistent with a lot of the beliefs in the literature. So people believed the larger learning rate will give you a flatter minimum, but there was no rigorous proof, and this is a rigorous proof. Okay, so in the remaining time, let me move on to optimization, but maybe I should pause and ask whether there's any questions or comments. Okay, great. All right, then let me talk about optimization. So here I'm changing gear to study basically the optimization of a function defined on Riemannian manifold, and in particular I'll be focusing on something called a Stiefel manifold. If you have heard me or Tomoki Osawa talking about another work of ours, namely optimization on Lie group, this work is different. That's because Stiefel manifold is not necessarily a Lie group. So what exactly is Stiefel manifold? So a Stiefel manifold is basically a set of tall matrices. So n by m matrices that are orthogonal. So what I mean by orthogonality is that, okay, so you have n by m matrices, and I require each column to be orthonormal to the other columns. So that means that, this matrix has to satisfy this quadratic constraint. And in a special case, when n is equal to m, then you actually recover something called an orthogonal group, which is a Lie group. So it is a group, but in general, if you have a tall matrix, it's not a group. And why do I want to optimize a function defined on Stiefel manifold? So here is a motivating example. It's very simple. So suppose you have an n by n matrix A. N may be huge, and I want to find its top m eigenvalues. So the largest m eigenvalues, n may be small. For example, so in machine learning and data sciences, maybe n is like 1,000,000 and m is like 10. And this is computationally very non-trivial in this case, because I mean you don't want to diagonalize things, etc. So you are wasting your energy because you just want a couple of leading eigenvalues, and you can solve it by formulating the problem as an optimization problem. So basically you do this optimization problem where X is actually an element of the Stiefel manifold, so such a matrix. And what it encodes is basically orthonormal basis of an m-dimensional subspace of the n-dimensional space. And then what this operation inside does is it basically projects this matrix A onto the subspace. And then the trace basically sums up the eigenvalues projected onto this subspace. And then you look for basically the best subspace such that the projected eigenvalues sum up to the largest. So this subspace, of course, gives you basically the largest m eigenvalues. Okay, so that's why you can formulate the problem as a Stiefel optimization problem. And one thing that is very important is that you need X to be exactly on the Stiefel manifold. You don't want to use a regularizer. You don't want to use approximation. If you use that, you break orthonormal basis, and then you can get very, very weird results. And if you think, okay, so if you think this is a problem that is too easy, for example, you may say, oh, this is a quadratic loss. How hard can it be? It's harder than you thought because the manifold is actually curved. It's a nonlinear space. So this problem is not even convex. But if you still think it's easy, here's a harder one. So it's based on a problem called projection robust Wasserstein distance. So first of all, what is a Wasserstein distance? So suppose you have two probability measures. You can have various ways of measuring their distance. Wasserstein distance is one of them, a very powerful one. It's basically defined in this, so this is one definition of Wasserstein distance. And basically the idea is that you have a pile of sand whose shape is given by mu, this density function mu, and then you want to reshape it into another shape. So you want to move it to another pile with shape given by this density nu. And then, of course, what you want to do is you want to minimize the amount of sand you move. You want to minimize the distance. So you can formulate the problem as sort of like an optimization problem where you basically minimize over all possible ways of moving the sand together, and then there's an associated cost. This quantity is unfortunately very, very costly to compute if the dimension is very high. There are various approaches proposed to remedy this difficulty. So here is a beautiful one created by a collection of experts. So it's called projection Wasserstein distance. The idea is that, okay, so your probability distribution, mu and nu, may actually have low dimensional structure. So you can actually look for a projection from a high dimension, projection from n dimension to m dimension. And then maybe once you have such a projection, you can compute the Wasserstein distance between the projected distributions, and then you optimize over all possible projections. So if you formulate the problem, you do some math, you can you can turn the problem into this max minimization problem. And this is computationally much more manageable if m is much smaller than n. Plus, they actually argue that this is an approach that is more robust because maybe, okay, so in n dimensions, you may actually have low dimensional structure. Say maybe n is 100 and m is like 3. But then you have an outlier. You have a couple of outliers that sort of spread over all the 100 dimensions. And then it's very hard to detect the low dimensional structure. But if you believe there's a low dimensional structure and then do the projection, you will automatically delete the outliers. You will get rid of the outliers, and then the result will be more robust. So that's roughly speaking the intuition. But again, you see, okay, so you have to do a maximization over sort of like this projection, which is represented by an element in the Stiefel manifold, corresponding to orthonormal basis of the m dimensional subspace. So so again, you have to do this optimization, and you have to be exactly on the Stiefel manifold. Okay, finally, I want to spend sufficient amount of time on this because this is new to us. This is actually newly introduced by us. This is the last example that I wanted to use to motivate the Stiefel manifold optimization. So it's based on basically an attempt to improve transformer. So what is a transformer? So in a nutshell, a transformer is a very, very recent but extremely powerful machine learning architecture. And the transformer was first introduced for natural language processing. So it basically deals with sequences. But later on, it was generalized to computer visions as well, and it sort of dominated both areas nowadays. And it's based on something called attention mechanism. So what is attention mechanism? It basically tries to improve recurrent neural network, which has a short reference window. For example, things like LSTM and GRU were invented to give you a longer reference window. But the attention mechanism actually has infinite reference window. So that's why it became very powerful for natural language processing and then computer vision and other applications very soon. So the way it works is that it has something called an attention layer. So it's called a multi-headed attention layer. And what it does is, roughly speaking, it tries to characterize long-range interactions between words in your sentence. And mathematically, how that works is that, okay, so each attention head basically has trainable parameters, like these weight matrices. And roughly speaking, these matrices characterize interactions between words. Of course, you don't really know them a priori, so you have to learn them by training. And then we ask ourselves, okay, so if they sort of characterize correlations between words, maybe we want to actually make these matrices orthogonal. So that you don't really double count correlations, so that you actually have more efficient characterization of the correlations of the interactions. And then we tried this idea. So it basically requires replacing the original optimizer, which is in Euclidean space, by optimization in Stiefel manifold. So we tried this idea. We tried it on something called vision transformer. And we found great results. So I can take the original vision transformer and add orthogonality, and then I will get much, much better performance than the original Euclidean version. And of course, vision transformer was very, very popular. So a lot of later on work actually followed up. So there are fancier models that have better performances. We don't even have to do any of these fancy things. We just add orthogonality, and we can actually even outperform the later fancier models. However, there's one catch. The catch is that we get good performance only if we actually train these weight matrices by our optimizers. There are existing Stiefel optimizers they may actually give you, they don't always give you worse results, but sometimes they even give you results that are worse than the Euclidean version. So, so what is going on is not exactly clear, but we tend to think that this is because our optimizer actually has better performance than existing optimizers. Okay, so hopefully I give you enough motivation about why we want to optimize on Stiefel manifold. This is not just a mathematicians made up example, made up problem. It's really important to machine learning. The question is how we do it. So we will use a variational approach. So the reason is it's going to be very friendly to non-Euclidean spaces, and also it naturally allows us to introduce the notion of momentum. Of course, you may ask, what is momentum? So it's really something that comes from mechanics. And you can't avoid Newton when talking about mechanics. So Newton said, okay, so the rate of change in momentum is given by the force. And you can turn this into differential equations. So you can define momentum. And then the rate of change of momentum is given by the force. If you choose a conservative force, so if you view this F as your potential energy, then the force is actually negative gradient of F. So this is basically Newton's equation. And then Lagrange came along. Lagrange said, okay, so you can also define a variational principle, meaning, okay, so you first define an action function. No, it's a function of function. So Q is a function of time. So Q is a trajectory. And then you can define S as a function of trajectory by simply integrating something called a Lagrangian evaluated along the trajectory. And if you let the Lagrangian be kinetic energy minus potential energy, and then you create this action functional, and you look for its critical point. So you solve this variational principle, and then you get exactly Newton's equation. So you have a minimizer of this action functional if and only if you actually your trajectory satisfies Newton's equation. You may wonder, okay, how is this relevant to optimization? So far, there's no relevance. And the reason is because actually the Lagrangian has a time translational symmetry. So it's invariant, it's independent explicitly on time. So as a consequence of the symmetry, you actually have a conservation law. So the total energy of the system is actually a conserved quantity. So when you run this dynamics, what you will see is the kinetic energy will constantly exchange with the potential energy, and F will not be optimized. But the reason you see is really because you have no time dependence of the Lagrangian. So in a beautiful paper by Vibisono, Wilson, and Jordan, they actually broke this time translational symmetry by multiplying L by some explicit time-dependent function. And then you can write down the Euler-Lagrange equation. It'll look like this. You have this new term. If you write down everything into a first-order system, you see, okay, so again, the momentum changes according to a net force, but now you have a conservative force plus an additional dissipative force. So as a consequence, you can prove that Q actually converges to a minimum of F guaranteed. So that's why this optimization dynamics in continuous time is actually doing the optimization. But then you can also get numerical algorithms. So in fact, if you choose gamma to be 3/t and you discretize the time of this system in a very specific way, you recover a celebrated method in convexity optimization called Nesterov accelerated gradient for convex functions. If you choose gamma to be something else, one discretization gives you another celebrated method called Nesterov accelerated gradient for strongly convex functions. And another discretization gives you heavy ball. And everything should be contrasted with gradient descent, which is a forward Euler discretization of gradient flow dynamics. And of course, on the right, gradient descent and gradient flow don't have momentum. And in fact, as a consequence, for example, you can actually get acceleration. For instance, take NAGC, where C stands for convex. So if your loss function is convex, you can prove that NAGC actually converges like 1/k squared where k is the number of iterations, but gradient descent only converges like 1 over k. So that's why momentum actually is commonly believed to give people to give us acceleration in the optimization. So everything that I said so far was great work that was already done in the literature. What I want to do is to generalize things to Riemannian manifold. And to generalize to Riemannian manifold, we will have to do something. So in fact, if you stare at the set of differential equations and try to generalize it to Riemannian manifold, it's not that easy. But if you use the variational approach that I mentioned, the generalization will be easier. So let me actually elaborate a little bit, and then I think I should be done very, very soon. I'll skip the details. Okay. So in a Riemannian manifold, first of all, you should ask, okay, so if you want to use a gradient-based method, what is a gradient? So here is an example that shows why this is non-trivial. So if you consider 2 by 2 orthogonal matrices and take a toy loss function as the determinant, and then what is the gradient? A careless person may say, oh, you compute the determinant and then you collect all the partial derivatives, and that's your gradient. But the truth is, okay, so the determinant of an orthogonal matrix is actually either +1 or -1. And in fact, on each connected branch, it's just a constant value. So the gradient should really be 0 everywhere. So why the discrepancy? Well, the reason is because the Stiefel manifold is actually a one-dimensional manifold. It's not four-dimensional. The ABCDs are not independent from each other. You can't really collect the partial derivatives. Okay, so that's just the tip of the iceberg. Why manifold optimization is a profound field. I would say more or less that the momentumless case, so the case without momentum, is very well studied. What we want to do is to actually focus on how to add momentum in a way that gives you very fast speed and also good accuracy. So again, it's based on variational principle. So we saw that in Euclidean case, you define the Lagrangian to be like this, and then you can get optimization dynamics in continuous time. If you have a Riemannian manifold, I intentionally replaced the Q by G, which is the trajectory on the manifold, to emphasize the difference. But basically, it's the same. So your Q dot will be in the tangent space. And if you have a Riemannian manifold, you can use a metric to replace the previous notion of kinetic energy, and then you get something like this. And then in theory, you can still do the variational principle. The corresponding Euler-Lagrange ODE will be giving you dynamics that does the optimization. In practice, this will be very implicit. So the expressions you get may not be very explicit. And later on, you have to discretize the time. It's going to be a nightmare. So what we do is we actually use a constraint variational principle. So let me finish this and then I'll be done. So previously we had this Lagrangian, and we want to do this variational principle. It sounds easy, but it's hard. The reason is because you do variation in a function space that is curved. So you require your function to be actually in the tangent bundle of the manifold, meaning x has to be on the manifold, x dot has to be in the tangent space at all time. What we can do is we can actually add a function Lagrange multiplier to enforce the constraint at all time. And then as a consequence, we can do variation in an unconstrained flat function space. And even after doing this, it's still non-trivial because you don't know what lambda is. But we actually have additional machinery to actually express lambda in terms of x, and then we will get explicit ODE in Euclidean space. For example, so okay, let me skip the geometric thing. So the ODE will look like this, and this ODE is always going to be giving you a solution that is exactly on the manifold. So you don't have to worry about anything. You can pretend x and q are just the matrices. So in the embedded space, but if you run the dynamics, you stay on the manifold. And also you have guaranteed convergence to the local minimum. So the hardest part is to actually discretize the time of these dynamics. So for the sake of time, I'll completely skip this. But this is really the key contribution of this work. So it's very technical, so I'm happy to tell you offline. But this is basically what I want to say. So by using a variational principle on manifold, we can hope to get optimization algorithm, but that's not enough. So we actually changed the variational principle to a constraint variational principle on Euclidean space, and then we get continuous optimization dynamics on Euclidean space, which automatically stays implicitly on the manifold, and then we discretize it in a way that preserves the manifold structure, and then we get accurate and efficient gradient descent with momentum for Stiefel manifold optimization. So that's all I wanted to say. So I want to thank my collaborators, and if you want to know more, feel free to scan any of these two links. So this is our blog, this is my Twitter, and thank you all for your attention and feedback.
Thanks a lot. This is a very, very nice talk. Thanks a lot. So any questions? Because a time maybe we can allow have some short questions. Any questions? I do have a couple questions.
Please.
So maybe Molei, we can talk. Will you be free after this? Maybe we can have some conversation.
Yeah.